Good afternoon, ladies and gentlemen, boys and girls. I'm David Walker and I work for Cambustion. And this afternoon, I will be telling you how to measure the mass distribution of an aerosol without any charging model. What I mean by mass distribution is shown here. So that's mass on the x-axis, concentration on the y, and the area under the curve represents the total mass of the aerosol distribution, which allows you to make some fairly meaningful comparisons between different aerosols. And at the same time as doing that, I'll also show you how you can measure the mobility spectrum. So the place to start is with an aerosol instrument for measuring aerosol mass, such as the Cambustion CPMA. Now, this instrument works on the balance of the centrifugal force, which is related to particle mass, and an electrostatic force, which depends on how much charge you put on the particle. So what you're getting there, these particles on the right screen, because they have the same mass to charge ratio, would all be classified the same by this analyzer. This leads us to a number of problems, which I'm going to address and talk you through. The first one is how you get the charges onto the particles. And the uncertainty in doing that. So if these graphs show a couple of different ways, we've got a bipolar charge distribution here, which shows different charging for different morphologies. And you also, depending on how you charge, whether it's X-ray, radioactive, or some sort of unipolar diffusion charging, you'll put different numbers of particles, charges on the particles. And if you don't know that, you'll get the wrong answer. The solution to that problem is to just measure the charge per particle. And to do that, we use an aerosol electrometer and a CPC particle counter. The CPC, of course, gives you the number of particles, and the electrometer gives you the number of charges. Dividing one by the other and accounting for the charge of the electron gives you the average charge per particle. This does rely on a tight charge distribution, which we'll see later. The second problem with the CPMA is what happens to uncharged particles. So if we take, for instance, a set point on this transfer plot of the CPMA of, say, 200 nanometers mobility, you will get, this is for a bipolar incoming charge distribution, some singly charged particles of the size you were expecting, some doubly charged particles, but you'll also get some uncharged particles that can penetrate through the classifier. If they're very light, you'll see these are small particles, because the centrifugal force is very low on those, and they're particularly significant at the highest size set points where the centrifugal force is quite low. So the solution to this is to basically get rid of those uncharged particles. And you can do this with a unipolar diffusion charger, such as the Cambustion UDAC. This is best shown by this charge distribution down the bottom. Up at the high sizes, you're putting, well, if you go up to a micron, you're getting sort of 100 charges per particle. But really what's important is down at the left here, where you'll see anything above about 20 nanometers is guaranteed to have at least a charge on it. This dramatically reduces any uncharged particles around, and as a result, those don't penetrate through the CPMA. The added benefit of doing this is because the CPMA is working on a mass to charge ratio. As the amount of charges go up, the amount of mass you can measure also goes up, because that you're limited on a mass to charge ratio, not on an absolute mass. Coming on to the third problem is a little more subtle and requires some understanding of how the CPMA works. You've got this balance of centrifugal and electrostatic forces across an annular gap. So a particle of just the right mass to charge ratio would take this trajectory down the middle where those forces are exactly balanced. But consider a particle that's just a little bit larger, starting at the inner wall. That'll have a slightly higher centrifugal force, which will slowly pull it to the outside. And how quickly it reaches the outside will depend on how draggy the particle is, or its electrical mobility diameter. And the reason this is important is because if you're trying to plot that mass distribution, you need to know the transfer function width of the CPMA, which is illustrated by these triangles here. The solution to this is rather clever. What you take is that flow into the electrometer and split it based on its electrical mobility. And we can do this with a device very similar to a DMA. So there's a clean sheaf flow coming in along with a sample and a central electrode, which pulls those charged particles across into the middle. But unlike a DMA, we're not aiming to trap any of those particles. We're aiming for all of those particles to pass out of either of the two outlets and then go to two more aerosol electrometers. Summing those two electrometers will tell us the total charge on the particle. And again, dividing by the CPC, we still get that average charge per particle measurement. The sort of bonus to this is you are measuring mobility diameter, and we know the average charge, so you get the particle diameter at the same time. What does that look like put together? What we've got here on the left is the schematic view and the cold glory reality on the right. So I'll talk you through it from left to right, schematically, and up to down in reality. We start off with the UDAC, where we place lots and lots of charges onto our particles. The CPMA provides us with a monodisperse aerosol of known mass to charge ratio based on the speed and voltage of the CPMA. That goes into the CPC, which counts for the number of particles. It also comes into the mobility separator, which I will just point out on this picture. It's this small silver thing up here sat below the CPC, which is really only not much bigger from the size of your fist. That splits into two aerosol electrometers, which tell us the total number of charges, divided by the CPC, gives us the average charge. Take the electrical mobility, times it by the average charge, gets the diameter. Take the mass to charge ratio, times by the average charge, gives us the mass. How that works in terms of the data processing looks a bit like this. So up here on the left, we've got the CPMA scan. So this is stepping through from a lightweight particle, that means running at a high speed, down to a large heavy particle, which means running at low speed where the centrifugal force is lower. And with relevant equations give us the mass to charge ratio along that scan. Now through that scan, we log the CPC and electrometer currents, and those, as you can see, increase in the middle and then drop off. Now what I didn't mention earlier about the mobility separator is those two electrometers are used to control the rod voltage to give you equal current in both electrometers, maintaining good signal to noise ratio. That's just done by a simple PI feedback loop. And you can see they're well in control all the way across there. There's also some uncharged particles measured down the bottom, and those are insignificant. What we get on the mobility separator, meanwhile, is just the voltage across the scan, which doesn't change by very much because the electrical mobility is not really changing. And from that, we calculate the electrical mobility. But back to the concentrations, if you divide the electrometer by the CPC, you get this average charge per particle plot. Taking that with the mobility separator gives us electrical mobility gives us the particle diameter. Again, taking the average charge and the mass to charge ratio gives us particle mass. Connecting all of these things together, we can calculate the CPMA transfer function width. And now we have all of this information, we can calculate the mass spectral density. Now, if we look at what that is in a more useful presentation, how do I get back to my presentation? Okay, we get, well, first look at a diameter distribution. So this is what you're familiar with from a SMPS, for instance. We've got mobility diameter on the x-axis and a normalized density on the y. But there are some important differences here between what you might get out of an SMPS. Firstly, we're getting up to well above a micron, or up to 4 microns. And the other thing is there's no multiple charge correction going on here because we're measuring the charges at all times. So there's no assumptions. What I will draw your attention to is the left-hand tail of these, which in some cases is not very resolved, and that's due to coming up against the maximum speed the CPMA can run at for this sample flow, which for these scans was 1.5 liters a minute. I should also just mention that these 4 lines are for 4 different aerosols. We've got 2 spherical particles and 2 different combustion agglomerates. Now, if we move on to the mass distribution, which you'll notice tells quite a different story to the diameter distribution you've just seen. And in some ways, this is a more interesting distribution because it allows for fairly intelligent comparisons between different aerosols. So what I'm saying here is the area under each of these curves represents the total mass in the aerosol distribution, and I've normalized all of these to be equal, which means you can compare them sensibly. In this case, it's the right-hand tail which is challenging to resolve. In one case, we're up against this time the minimum speed of CPMA, but in general, the signal to noise is getting problematic because you're fundamentally counting a small number of very large, heavy particles, and that means there's just not a great deal of signal around. Of course, we've got mass and mobility, so if we divide the two, we get the effective density of the particle, and plotted on this log-log graph, the gradients of the lines tell us about the shape factor of particles. So the two spherical aerosols have shallower lines, and the two combustion agglomerates have rather different gradients. Finally, you can also get the charge distribution out, which is perhaps less immediately interesting, but does give us some justification for needing to measure this, because even quite small differences here add up to meaningful differences in the mass and mobility diameter. Great, you may say, but do you believe the results? So there's a couple of ways we can go about convincing ourselves this is telling us the truth. And the first way is because we've got a mass distribution, we can integrate that up across the distribution and give us the total mass, and that is something we can weigh by collecting an aerosol on a filter paper and measuring on it on nothing more sophisticated from a set of sensitive scales. So here we've got a cast combustion aerosol source. There's a couple of extra components I'll just point out. There's a rotating disc diluter to lower the concentration so that it's within the working range of the CPC, and there's an electrostatic precipitator to just keep an eye on those uncharged particles. And the numbers over here are really rather good, in fact, better than I would hope for. And I think some luck has been involved because I'd expect a result within maybe 20%, looking at the uncertainties of the instruments, and this is within, well, 1%. There has been some particle loss correction, so I expect about 10% in the UDAC, maybe 20% in the CPMA. And probably the uncertainty in those has fed into the fortuitous result. The other obvious thing to check is take an aerosol of known shape, so a sphere, and a known material, in this case oil, and look at its effective density across its size range, of which you'd hope it was always the same. And that is more or less what we've got. Although there is some error here, which after making this measurement, I've traced to a non-linearity in a prototype voltage supply, so I'm not concerned about that. Which I think leads me on to my summary. So what we've got here is a new instrument for measuring aerosol mass and mobility, which we've dubbed the mass and mobility aerosol spectrometer, or the M²AS. And this allows simultaneous measurement of mass and mobility, unlike other techniques which require some sort of tandem scan, which is very slow. However, there is a potential flaw, which is in some bipolar distributions or multimodal set aerosols, if you get an overlap, in this case in the mass to charge distribution, what you assume is monodispersed coming out of CPMA will no longer be, and that will upset your mobility measurement. However, we are measuring this all without a charging model, which particularly for non-spherical particles such as combustion agglomerates is a real improvement in accuracy. We've also got quite a wide measurement range spanning, well, nearly 5 orders of magnitude in mass terms. Now, I'll just point out some areas of improvement, of which there are a few, but the main ones are the scan is relatively slow at sort of 10 to 15 minutes to work through those CPMA speeds. And that could potentially come down to sort of 2 to 3 minutes with a continuous scan like you get on an SMPS or now on the AAC. But that would require some slightly trickier maths, which we haven't got around to yet. So with that, I think I'll ask for your questions. And I'll acknowledge my summer student as well, who helped us with this, Matt Pengelly.
Great, thanks so much, David. We have time for 1 or 2 questions if there are any. You can use the raise hand function at the bottom of the participant list. Yeah, so Peter Knapp, you have a question?
Hi, I had a question about the particle losses to the walls. If they're charged, would that create a surface charge on the instruments?
So this is presumably back on the mobility separator. So the idea is there are no particle losses through this, because by careful selection of the flows, and because this is effectively a monodisperse aerosol coming in, the particles are drawn into this clean sheath flow, but they never make it as far as the wall. And by the time they get to the bottom, there's no longer an electric field pulling them across onto the wall. So they just sit in the flow and drift out to the electrometer. So the losses, there aren't any losses.
The very, very small particles don't, the Brownian motion doesn't dominate to cause them to pass over the sheath flow and hit the wall?
No, they don't. Brownian motion isn't significant for these size particles in this analyzer.
Oh, thanks.
Great, thanks. And then Simone Hoshgrab also has a question.
Hi, that goes to that same slide. I was just trying to understand exactly what your strategy is for the split. You just say high and low, and I understand you said that you monitor the 2 currents to make sure that the mean is the same. Is that what the trick is? I may have missed it.
So they overlap.
Okay, so right, yeah. So we've got these 2 electrometers which we're measuring, and those are controlling the voltage of this center electrode. Now, because the transfer function of this is very broad, you always get, even if you feed in particles of exactly the same mobility, you'd always expect half of them to come out of either side if you pick the right voltage. So maybe this also might help. So this is, the blue line is the voltage of that central electrode, which is changing over the course of a scan in order to keep the 2 electrometer currents on top of each other, even though the actual electrometer current is changing. The ratio between the 2 is kept constant, well, is kept equal. Does that explain it?
I'll have to think about it, but thanks.
Okay, yeah, it takes a bit to get your head around it for the first time.
All right, great. Thank you so much, David. I appreciate that. And we will now move on to our next presenter.